Okay, let's get started. Assignments, everything going all right? Assignment 6, refactoring, object-oriented programming, good times. Differentiable robot design for the grad students. I realize I went way too fast and way too deep last time on differentiable robot design. We will come back to that in lecture 24 towards the end of the semester. So if you didn't pick up everything last time about differentiable design, not a problem. We'll do it again at the end of the semester. Okay, so where are we? Where are we going? We're making our way through the history of the field, relatively a short history. We were almost finished lecture 8 last time, looking at continuous time recurrent neural networks. Building neural networks that are composed of neurons and synapses that are more biologically realistic than probably you're familiar with, which obviously leads to a more complicated neural network composed of, in this case, ordinary differential equations. We went through each term in this ODE one by one last time, pointing out why each term is in there and what aspect of biological nervous systems that particular bit of math is trying to capture. Okay, so just a refresher, we have a CTRNN, we have N neurons inside. Each neuron has its own ODE, and when we're talking about any individual neuron, we're talking about the ith neuron, this is the equation that describes its behavior. CTRNNs were used in a lot of the early experiments in robotics and are still used to this day. That's why we're spending so much time talking about them. And they have an interesting property. They have several interesting properties that can be exploited specifically by robots that are trying to acquire adaptive behavior. And we ended last time by looking at this particular robot, which is controlled by a CTRNN. We're going to talk about this experiment for the next few minutes. This robot is not just learning how to do things in the world, like manipulate this cube, but it is trying to learn how to acquire and then sequence motor primitives. So a motor primitive is a term we're borrowing from neuroscience. It's a little bit of your brain dedicated to a very simple, short behavior, taking one step and then sequencing those motor primitives together to produce walking. To learn how to strum a chord on a guitar, that's a motor primitive. Sequencing them together in a song, that's a sequencing of motor primitives. All of the complex adaptive behaviors that you are capable of, they are hierarchically arranged. They are made up of simpler motor primitives, which in turn are made up of simpler and simpler and simpler motor primitives. So if we want to try and teach robots ever more complex behavior, it's probably best not to try and teach them from scratch every time to acquire a complex behavior. Teach them simple motor primitives and then give them the ability to learn how to put them together in different sequences. That's what we're going to look at in this experiment. Okay, so those are the motor primitives. How are we going to go about doing this? Here's a little cartoon. Again, it might be difficult to see in the back of the room here. Here's what we want the robot to do at the end, after it's evolved the ability to do these simple motor primitives, like move the block up and down, move the block left and right, move the block forward and back. We should be able then to command it to put them together in arbitrary sequences. So here's the robot in the home position, yet another motor primitive. Reach for the object, another simple motor primitive, and then we ask it to do one of these and then go back to the home position. Okay. The title of this research paper that we're discussing today, it's a bit of a mouthful, Emergence of Functional Hierarchy. So remember, we're hierarchically composing motor primitives in a multiple timescale neural network. They're going to exploit the fact that CTRNNs have this tau parameter associated with each neuron. By setting that tau parameter to different values, the investigators can slow or speed up how neurons change over time. Okay, what does that have to do with motor primitives? Well, if we want to try and teach or train or evolve a robot to learn simple things and then compose them together hierarchically, The simplest thing you would probably imagine, or most people imagine when they think about how to solve this problem, is let's make a brain for our robot that looks something like the picture down here. Let's assume we have 3 different motor primitives. The green is shake the block up and down 3 times, the red is shake the block left and right 3 times, and the blue is shake the block forward and back 3 times. Red, green, blue, 3 different motor primitives. Let's create 3 separate neural circuits inside the robot's brain and then train it or evolve the parameters of the green circuit so that when the green circuit grabs control of the motors, it causes the robot to shake the block left and right. Let's train a separate neural circuit, a separate subset of neurons and synapses inside the robot's brain. Let's train that when that neural circuit is in control of the motors, it causes the robot to shake the block up and down 3 times, and so forth. Does this particular approach sound familiar to you? We're going to create different little neural modules, and then we're going to let them have control of the motors for a little bit, and then release control of the motors when that particular neural circuit should not be in control of the robot anymore. Sound familiar? Anybody have a Roomba at home? The Roomba is controlled by a simple Bradenberg vehicle turned towards the dirtier half of the room, turn towards the other dirty half of the room. Basically, follow the dirt, unless you hear a cat's meow or you sense that you're about to go over the top of the stairs. There are sensors on board the Roomba robot that if something more urgent, like you're about to run over the cat or fall down the stairs, that particular neural circuit, the turn away from the meowing cat or turn away from the fact that I don't feel anything under the front of my body, those circuits take over control of the motors and turn the robot away from the cat or the stairs. That was the subsumption architecture that we saw towards the beginning of the course, invented in the 90s, a very simple and very intuitive way to do things. Hopefully at the moment, most of your brain is dedicated to what you see up here and what you're hearing me saying. You're thinking about evolutionary robotics. But if there's a fire alarm, you will immediately hopefully forget everything that's happening up here, and a different part of your brain will take over. The part that's there to make sure that you stay alive. It's important that that part is able to take over control of your muscles at a moment's notice. Yeah? Makes sense, feels intuitive. Not what the researchers did in this case. What's the problem with this approach? The advantage is it's simple, it's intuitive. What's the problem? How many motor primitives are you capable of? Maybe more than 3. You know how to safely extricate yourself from this room if there's a fire alarm. You probably know how to safely extricate yourself from that room if there's a fire alarm, and that room, and that room, and that room. How many motor primitives are you capable of? Sorry? Many, 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 many. You don't have a lot of real estate in here. We've talked about this before. This needs to get through the birth canal. There's only so much neural real estate. If every time you wanted to learn a new task, your brain or your body had to grab some yet new part of your brain and use that real estate to train that behavior, not a very scalable solution. At the moment, current state-of-the-art robots, they're capable of 100, maybe a couple of 100 motor primitives. They're nowhere close to us yet, but hopefully in the not too distant future, we can create robots capable of thousands, tens of thousands, millions of motor primitives. We don't want to have to carve out a new bit of neural network or a control circuit for the robot. It doesn't scale very well. So is there a way that we can train a machine to be capable of learning more and more motor primitives and then stitching them together in arbitrary sequences without having to add more neurons and synapses to the robot's neural network controller every time we dream up a new motor primitive and try and teach it to do that? That's the question that these authors were asking themselves, and they answered it by exploiting the time constants in CTRNNs, and this is their cartoon explanation for how this works. What they're going to do is they're going to create a CTRNN for this robot, and they are going to allow evolution to set all the W's, all the G's, and all the thetas, so that the robot shakes the block left and right, up and down, forward and back. But the human investigators are going to be responsible for the taus. What they're going to do is set the taus of some of the neurons in the CTRNN to very, very, very low values near zero, which create Woody Allen neurons that can change their values very quickly and are very sensitive. They're then going to evolve these parameters so that the robot, given some input signal to the CTRNN, an input signal is going to say, shake the block left and right, and they're going to evolve the robot so that these fast neurons cause the robot's arms to do this. Up till now, when we've talked about neural networks embedded in robots, we've talked about those robots having sensor neurons, sensor neuron 1, 2, through N. We're going to add an additional input neuron to the CTRNN, which is the teaching neuron. The investigators can set this teaching neuron to 0, and that's the teaching signal saying you should shake the block left and right. As evolution is proceeding and evolution is mutating and crossovering a bunch of W's, G's, and thetas, maybe the robot does a very poor job at shaking the block left and right when it has a teaching value of 0. Those CTRNNs get a low fitness value. They're deleted from the population of evolving CTRNNs. Some of those CTRNNs are going to allow the robot to do a little bit better job of shaking the block left and right. They get a slightly higher fitness value. They survive and produce offspring until eventually, whenever you set this input neuron to 0, the robot does this with the block. So far, so good? Okay. They continue evolution by then putting in a teaching signal of 1, where 1 means shake the block up and down. The robot maybe does a poor job of that. They continue evolving, and then they start, during evolution, switching. Sometimes they put in 0, sometimes they put in 1, and the evolutionary algorithm watches the robot. How well does it do at shaking the block left and right? How well does the robot do at shaking the block up and down? So far, so good. Once fitness gets high enough that the robot correctly exhibits these two different motor primitives when told to do so, now they throw in the third one, shake the block forward and back. Keep evolving, now throw in 0, 1, 2, and they keep going until they evolve a CTRNN with an appropriate set of W's, G's, and thetas that will cause the robot to do any of these 3 motor primitives on command. So far, so good? Okay, that's great. The robot is now capable of 3 motor primitives, but it is not yet capable of putting them together in a unique sequence. We can force them to do left, right, then up and down, then forward and back by putting in 0, 1, and 2, but we would like the CTRNN to be able to do this on its own. So how do they do that? They throw in, at this point, a bunch of additional neurons, and they connect those neurons to the fast neurons with some synaptic weights. These particular neurons, the human investigators set the tau values to be very high values, which causes these neurons, whatever they do, to change their values slowly. And now they continue evolution where they can feed in a vector. And now the robot will slowly do left, right, forward, back, up and down, or left, right, forward and back, up and down in arbitrary sequences. What are these slow neurons evolving to do? These slow neurons are responding to the teaching signal, and they push the fast neurons into an attractor. What do I mean by push into an attractor? What I mean is that, as you can see in the purple here, the purple is meant to represent the activation, the amount of value inside a single slow neuron. As that value is slowly changing over time, that value, for example, y sub j, is flowing via the W's into the fast neurons and causing them to change values. It might be that this slow influence from the slow neurons messes up what the fast neurons can already do. They're already capable of individual motor primitives. They're Woody Allen neurons. They're very sensitive. They freak out all the time. The slow ones are here to push them and keep them in left, right, left, right, left, right. And then when a slow neuron changes slowly to another value, it pushes the neurons from a different direction. What do I mean by pushing from a different direction? The slow neuron's value, y sub j, has slowly changed to something else, which is changing the incoming values that the fast neurons receive, which causes changes in the fast neurons. And we're going to evolve all of the W's, G's, and thetas so that that change pushes them into up and down, up and down. Yeah? The metaphor here is imagine an orchestra. Every member of the orchestra goes off and practices their part of the symphony. They can play perfectly on their own. Now they're all brought together. They try and play their own piece, but they're hearing the music of all the other members of the orchestra, some of whom play a little bit faster or slower than an individual person, the ith person, is comfortable playing. So they're all kind of pushing each other out of sync, disrupting each other. So what do? They train to listen less to their neighbors and pay attention to the conductor who is telling everybody when and how to change to the next part of the symphony. The slow conductor pushes everyone into the right cadence or the right speed and indicates when to switch to another part of the symphony. That's the intuition. Make sense? Okay, let's see how this looks in action. I want you to ignore the teaching signal over here. I just want you to look at this bundle of spaghetti here. This is the CTRNN. We have a whole bunch of fast neurons here. They made these neurons fast by setting a tau value to 5. I don't know where they got 5 from. I don't know why it's not 3 or 0.001. They probably fiddled for a while until they got something that worked. What's important is that the tau values of these neurons here, the tau value is higher than the tau value of these. These are the Eeyore slowly changing neurons. These are the Woody Allen fast changing neurons. You can see the fast ones are all wired up. The members of the symphony can hear each other while they're playing, but they are also wired up to the slow neurons. They can hear the conductor as well. Now it is only the conductor that receives the goal signal or the teaching signal. These slow neurons are receiving through their inputs an integer. 0, 2, 1, 2, 1, 0, 1, 2. That's coming from outside. That's the human dictating in what sequence they want the motor primitives to be exhibited by the robot. The slow neurons receive this input, and the slow neurons slowly start to change their values in some way. And when this neural network is evolved, that slow change pushes the fast neurons into a particular pattern that influences these neurons, which are the sensor and motor neurons. These are the neurons that are directly responsible for controlling the motion of the robot. So far, so good? Okay. All right. What you are looking at here is the robot behaving. We're going to talk about each one of these panels. The top 4 rows, this is the robot's body behaving. And the 2 rows in the bottom here, which we'll get to in a moment, this is peering inside the robot's brain. We're looking at its CTRNN. Let's start by looking at proprioception here. We don't need to worry about the teaching signal here for a moment. Proprioception are particular type of sensors that report the orientation of the body in space. You have proprioceptive sensors all through your body. Without looking at your legs and feet, you can feel how they're arranged. When you change the orientation of your body without looking at it, you can feel how it's changing. That sensation, that feeling is being reported to you by proprioceptive sensors in your body. What we're looking at in the horizontal axis here is time. And you'll notice, you may not be able to read this in the back, there are labels on the top of the axis here saying up, down, then left, right, then back, forward. These are the goal or the teaching signals. These are the humans telling the robot, shake the block up and down 3 times. Now I want you to shake the block left and right 3 times. Now I want you to shake the block back and forward 3 times. We've got time on the horizontal axis here, and we have the value of the proprioceptive sensors from 0 to 1 on the vertical axis. What you'll notice is that when the robot is commanded to shake the block up and down 3 times, there's 1, 2, 3 bumps in the proprioceptive sensors. 1, 2, 3. The robot is feeling its arms go up and down 3 times. Left and right, there are more bumps. This is 1, 2, 3, and then 3 bumps here, backwards and forwards. You'll notice that there are obviously multiple lines in these panels. These correspond to different proprioceptive sensors in different parts of the body. What matters is that all of them are regularly changing 3 times. Yeah? So this is the data corresponding to this video. The robot is feeling its proprioceptive sensors going up and down 3 times. And then it feels its proprioceptive sensors again going up and down 3 times in a different way. That's proprioception. Okay. Okay, let's move on to vision. The robot is also watching itself shake the block up and down. There is a raw video feed that's coming into the CTRNN, which is being boiled down to a few visual features, which we won't talk about today. Remember the Sussex gantry robot that we talked about last week? We take a raw video feed. Instead of giving the CTRNN or the neural network all 10,000 pixel values, the investigators compress those numbers down and then feed that visual input into the robot. We're not going to bother talking about how that happens, but what you can see is whatever these visual features the robot is looking at, and it's looking at the block, it's whatever it's looking at, that thing in its visual field increases and decreases or changes regularly as it's shaking the block up and down. So the vision information over here, the visual sensor data is telling us that the robot is seeing stuff in its visual field changing with a regular oscillation, and it's feeling its body change with a regular oscillation. Putting these together doesn't prove that the robot is successfully shaking the block up and down. You'll just have to take my word for it that that's what's happening. Okay. What is much more interesting is what's going on in the bottom pair of rows. We have the same horizontal axis. So we've still got time on the horizontal axis down here. And again, this is very difficult to read. But on the vertical axis, we have some indices running from 101 to 160, and then 161 to 180. The CTRNN that controls this robot is made up of 180 neurons, which means there's 180 ordinary differential equations. There are 180 tau values, 180 gains, 180 thetas, and 180 times 180 weights to be optimized. Why does this graph start with 101? The first 100 neurons are the input-output neurons. These are the ones that are directly sensing the world and acting on the world. In this experiment, those are the least interesting neurons. We're not even going to bother plotting them. We're more interested in this group and this group. Neurons 100 through 160. These 60 neurons are the Woody Allen neurons, the ones that are changing quickly over time. So there are 60 rows in this panel. And sure enough, you can see if you squint across these 60 neurons, they're changing pretty quickly. So black means a very low value of that neuron. White means a very high value of that neuron. And if you look very carefully, you'll notice that there's regular patterns of activation. As the robot's arms are shaking the block back and forth 3 times, the 60 fast neurons, whatever they're doing, some of them are going down, then up, some of them are going up, then down, up, then down. Whatever individual pattern of activation those individual fast neurons have, it's tracking that. These are controlling, these fast neurons are pushing the sensor motor neurons and causing the robot to do this. So far, so good? Okay. The final 20 neurons are the Eeyore neurons down here. And you'll notice as you track from left to right, the values of these neurons are changing more slowly. So slowly that you don't really even see this fast 3 times oscillation during a single human-dictated command. They're changing more slowly. The conductor is holding all of these neurons in this pattern, and then slowly these 60 neurons change to a different pattern, and at the moment they do, they cause these fast neurons to switch into another set of coordinated fast oscillations. You'll see dimly that there's a little bit of this fast oscillation among the slow. They're not that slow. Over here, they switch to the slow neurons switch to yet another pattern and push these neurons into yet a different pattern of oscillation, which causes the robot to shake the block backwards and forwards. So we have a hierarchy here. We have a human saying A, B, C, B, C, B, C, A, B, C. The slow neurons are holding some pattern for all of A, all of B, all of A, all of B. And during each of those holding patterns, that holding pattern is pushing the fast neurons into a different pattern. And given this fact, we now have a robot that's capable not just of exhibiting or learning different motor primitives, but can arbitrarily put them together in different sequences on command. Why don't we end class early? Please leave the building. Please leave the room, then leave the building. I'll meet you at the cafeteria 5 minutes later. I'll buy everybody lunch, and then, right? I'm giving a high set of commands here to you. You'll hopefully be able to hold on to that sequence. And as you leave the room and leave the building and walk across campus, you're holding on to this sequence in your head. And that sequence, the current member of that sequence that you're executing, the leave the room command, all of the gazillion motor fibers in your body are firing at a very fast rate with a very fast oscillatory pattern as you walk out of the room. Once you leave the room, you switch into a slightly different motor primitive as you leave the building, and so on and so forth. Humans are pretty good at certain things. We're pretty good at this. With a lot of training, usually formal training, you can learn a lot of different motor primitives. How to play all the notes on a given instrument or all the basic plays in a given sport. And then as you get better and better at that instrument or that sport, you get better and better at composing those motor primitives into ever more complex hierarchies. A lot of other non-human animals on this planet, very, very good at large numbers of motor primitives. They're not so good at rearranging them in a flexible, nimble manner into new sequences of those patterns and continuously organizing them into ever, ever greater hierarchies. Not a lot of things that humans are better at every other animal on the planet at. This is one of the things we're pretty good at. Okay, and we are still figuring out how to teach robots to do that. Okay, that's it for lecture 8. Any questions about C-turn-ends before we move on? Okay, on to lecture 9 and minimal cognition. This is one of my more favorite lectures of the course for the following reason. The minimal cognition experiments were carried out 25 years ago now. They're still cited very often in the literature. They're a landmark in the literature for the following reason. You may remember that at the beginning of the course, when we talked about the early days of AI, a lot of researchers struggled because no one could come up with a good definition of intelligence, understanding, free will, comprehension, sentience, all these things that we feel like we have, that we want to build into machines, but we can't build it into machines because we can't formally define what they are. We're still struggling and arguing about that to this day. Does ChatGPT understand? Some people say yes, some people say no. Why is there disagreement? Because nobody has a formal, specific, generally agreed upon definition for what understanding means. So the authors of the minimal cognition experiments sidestepped this whole issue. They said, we don't care about definitions. What we're going to try and do is make the simplest possible machines we can, and we're going to equip them with the simplest possible neural networks we can, and we're going to then train them to do a bunch of admittedly simple tasks. But these are simple tasks that if you see an organism doing them, you'd start to say, okay, that organism has a little bit of smarts. If you saw an organism exhibiting 2 of these simple behaviors, one after the other, you'd say, okay, it's a little bit smarter. What are all the cognitive building blocks? What are all the simple things that we're capable of that indicates we are intelligent or we understand in some way? So for these researchers, like Turing, they have their version of the Turing test. This is like the physical Turing test. We're going to see a whole bunch of agents in the minimal cognition experiments, and they look like they're doing something that's kind of cognitive. Whether you then want to decide, yes, that's a cognitive or that's an intelligent robot, or no, it's not, it's up to you. It depends on your definition of cognition and intelligence. The authors of these experiments don't care. They're going to just try and evolve ever more cognitive building blocks into these agents to the point where they're eventually useful, and most people would probably attribute intelligence to them. That's the plan. That's the strategy. Still going 25 years on, by the way. Okay, we're going to look at 4 of those cognitive building blocks today, the first 4 that were reported in this paper back in 2000. Okay, what are some cognitive building blocks? What are some things that a generally intelligent agent needs to be capable of? From the perspective of these authors, one of the 4 is the ability to perceive affordances. When you look around your world, like in this room, for example, most of us would agree there's a lot of chairs in this room. If I then asked you, what is a chair? You'd probably say it's something with 3 or 4 legs. It generally has a flat surface about halfway up, and some chairs have a vertical surface on their back the rest of the way up. You'd give me a geometric description of what a chair is. You might remember when we talked about computer graphics and computer vision a few weeks back. It seems like we're not telling the truth. We give a geometric description for a chair, 4 legs, flat back. There's no verbs in that sentence. It's all nouns, geometry. There's a thing and another thing and another thing and another thing. But if you put somebody in a brain scanner over in the College of Medicine over here, and you ask them to describe a chair, and they give you that geometric description, and you scan the motor you scan the motor strip. It's the part of your brain that would be covered when you're wearing earmuffs. The motor part of your brain lights up as you're thinking about a chair, as you're hearing a story about a chair, as you're describing the geometric properties of a chair. If you're not using any verbs, you're just talking geometry, why is the motor part of your brain lighting up? Not only is the motor part of your brain lighting up, but a particular part of your motor strip is lighting up.
What is the motor strip? When you use your right arm, there's one part of the left part of your motor strip that lights up. When you use your left arm, there's a small bit of the right side of your motor strip that lights up. When you use your legs, there's another part of the motor strip that lights up. It's amazing, actually, when you look at the motor strip, every time a part of your body is activated, a specific part of that motor strip lights up. When you think about extending your right arm, the same part of your motor strip lights up as it does if you actually extend your arm. If you think about actions, your motor strip lights up. So you have someone, possibly yourself, in the scanner, thinking about chairs, talking about chairs, and a part of your motor strip lights up. Which part of your motor strip do you think is lighting up, and why?
Like one by your legs or something to like indicate sitting?
Absolutely. You feel yourself sitting in a chair, and then if your mouth is commanded to talk, somebody asks you to talk about it, you don't say, a chair affords me the ability to sit on it. When you look at this thing, you might think you're reasoning about it in a geometric way. Your brain isn't. Your brain is running some sort of simulation or a video game and it's simulating you walking up here, turning around and doing this, and your brain is trying to run forward. What will happen? Will you stop or will you tumble onto the ground? This was long before brain imaging was possible. Psychologists hypothesized about this, that this is what was happening. They were right. J.J. Gibson, very famous psychologist, J.J. Gibson came up with this term, affordances. Gibson argued, he didn't have the data yet to prove it, there now is data. He argued that when we try and survive and thrive in the world, we're looking and reasoning about everything all the time, but we're doing it based on how we think, we or an individual in general, what actions may be possible given that object. Another way of saying that, when we look at an object, what actions does it afford? Yeah. I deliberately picked 5 very different chairs, if you like, to prove that when we give a geometric description, it's usually a lie. It's very, very difficult to come up with a geometric description of a chair that includes all 5 of these exemplars. You might be capable of doing so, but you're really kind of stretching the illusion, right? Because that's not what our brains are doing. When you look at these 5 objects, especially because I've deliberately put them all together, these objects shout at you. They project an affordance. They say, we all have something in common, or your brain very easily discovers that they share something in common. They share a common affordance, which is sittability. Here's another 4 objects. What's the common affordance? Especially relevant on a day like today. Strong hint.
Energy.
These things generate energy. That description did not include you, and it did not include an action relative to the object. Imagine we put you back in the hypothetical brain scan, and I show you these 4 objects together. What part of your body is responding? Your brain is responding, absolutely. Your brain is always responding. Your motor strip is also lighting up. There is something you feel when your motor strip is assuming there's something common you'd feel as you interact with all 4 of these objects.
Like starting a fire.
Starting a fire? Okay, that is a verb that involves an individual. We're getting closer. Why do you start a fire?
To be warm.
To be warm. Which part of your body gets warm first? You're outside. The skin part of your motor cortex lights up first. You literally feel warmer, although you might not realize it, when you look at these objects in common. But when I asked you that, none of you gave me that answer to start with. Thinking about thinking is misleading. When you ask humans to give an explanation for why they did something or why they thought something, that we're not so good at. We confabulate, we make stuff up. But our brain, or at least certain parts of our brain, know. The real answer, if your motor strip was allowed to answer, these things make my skin feel better if my skin feels cold. That's what they do. Okay, that's an affordance. It seems like a very abstract thing, a kind of a weird place to start for simple robots. Here's our first minimally cognitive robot. It's a square. And in this case, they are going to evolve C-tyrannins for this simple robot to evolve the ability to perceive affordances. The affordances in this case, or the individual involved in the affordances in this case, is not you, it's from the agent's perspective. The agent is going to evolve the ability to reason about the affordances in its environment. What does it see, and what does it conclude about its relationships to this object? What kinds of actions does this object provide it, the agent, the individual? Okay. Again, what I really like about the minimal cognition experiments is they take all that airy-fairy abstract stuff and boil it down to something very simple and concrete. So here we go. Here's the agent. It's a square, and it's going to move back and forth along the bottom of the screen. All of the minimal cognition experiments look like 80s video games. You can think of like Space Invaders. We've got a little robot moving back and forth along the bottom of the screen. These two black arrows represent that the robot has two rocket thrusters. There are two motor neurons inside the C-tyrannin. If the left motor neuron has a very high value, the left rocket fires strongly and the robot moves to the right. If the second motor neuron inside the C-tyrannин fires strongly, has a very high value, the right rocket fires very strongly and the robot moves to the left. If both motor neurons are firing very strongly at about the same magnitude, both rockets fire and the robot doesn't move. Any combination of pairs of values of the motor neurons cause the robot to fly around left and right along the bottom of the screen. So far, so good? Okay, that's the motor neurons. This robot has 1, 2, 3, 4, 5, 6, 7 sensor neurons. Those sensor neurons, if you remember the C-tyrannин equation, the last term was uppercase I, lowercase subscript, lowercase I, terrible notation. Those 7 neurons, at every time step of the simulation, those 7 sensor neurons are receiving distance information. You remember we talked about infrared sensors that send out a beam of light and detect how long it takes for the light to get back. That's what these gray line segments represent. You can also think about these as like 7 whiskers. The robot is sweeping seven whiskers above itself as it moves back and forth at the bottom of the screen. Very, very simple motor system, 2 rockets, very, very simple sensory apparatus, 7 proximity sensors, and then a bunch of hidden neurons. Everything's wired up, a bunch of gains, weights, taus, and bias parameters. Okay? So we could take an evolutionary algorithm now and start evolving the parameters of those C-tyrannins to cause the robot to move in some way based on what its 7 proximity sensors do. So let's give it something interesting to do. We're going to take a pair of objects and place them at the top of the screen, and then at the beginning of the simulation, we're going to let go and let those that pair of objects start falling. We're going to evolve the robot such that if the gap between the pair of objects is wider than the robot should get underneath the falling pair of objects and allow the left and right object to fall on either side of it and not touch the pair of objects. Yeah? So if the gap is passable, I forget what grammatical term that is. What is that, an adverb? Passable, yes, an adverb. If it's passable, the robot should thread the needle. It should go between and let either object fall on either side. If the gap between the pair of objects is too narrow for the robot to get through, it should run away. Go to the left and get out of the way and let the pair of objects hit, or go to the right and let the pair of objects hit. So they're going to evolve this robot to perceive the passability affordance? Can I get through the gap or not? Can I, so there's the individual, get through, there's the action, the gap, something to do with the object itself. A very, very simple thing, but this is something you'd like robots to do. If there was a robot in this room, it should know that that's not passable and that actually is passable. Geometrically, they look kind of the same. They're about the same size. There's some reflective glass, but one of these objects affords to us passability and the other one doesn't. Okay. Any questions so far? Okay, let's have a look at the fitness function now. The fitness function is going to be called P for performance, the performance of the robot. A higher P, more performant, the robot's doing a better job, it's understanding this affordance better. Lower values of P are worse. First thing we're going to do is compute P by summing up a whole bunch of P sub i's. P sub I is the performance of the robot during the ith trial. Remember when we're evolving C-turn-ns for robots, we have a population of C-turn-ns, or we have a population of random weights, tiles, and so on, then another random set of weights, tiles, and so on. We take each C-turn-n, take it out of the evolving population, drop that C-turn-n inside the robot, let it do its thing, compute P sub 1, the first trial, reset the robot to some position at the bottom of the screen, put another pair of objects at the top of the screen, plug the C-turn-n back into the robot, and perform a second trial and compute P sub 2. What was the performance of the robot during that second trial, and so on. And then finally, after a number of trials has elapsed, compute P, the average ability of the robot to run away when the gap was impassable, and the average ability of the robot to thread the needle when the gap was passable. If the robot always threads the needle when the gap is wide enough, and it always runs away when the gap is narrower, these authors would say that robot understands affordances. You can't argue with me because I'm not using a definition. We're just pointing at behavior. The robot is passing this particular physical Turing test. It is acting as if it understands affordances, and for these authors, that's good enough. So far, so good? Okay. All right. So let's unpack P sub I. Let's start up here. Okay. So if the opening between the pair of objects is too narrow for the object to pass through, we're going to compute P sub I this way. If the gap is wider than the robot, we're going to compute P sub I this way. Okay, let's start with this one. Okay, so P sub I is going to be equal to 2 times the absolute value of D sub I. So now what is D sub I? D sub I is the final horizontal separation between the center of the agent and the center of the aperture at the end of the ith trial. So we have a pair of falling objects. We have the agent. If the agent is over here and the pair of objects falls 20 length units to my left, we're not going to introduce any actual units in this experiment. If the pair of objects falls 20 units to the agent's left, D is minus 20. If I go over here and the pair of objects falls 30 units to my right, then D sub I is 30. If I stay right here and the pair of objects falls directly on top of me, then D sub I is 0. Okay, not very good terminology either because they're using D for distance. Distance should always be a positive number, but I've just told you that D can be positive 20, minus 30, 0. So not great, but okay. So P sub I is going to be 2 times the absolute value of D sub I if the agent collides with the wall when the opening or the aperture is too narrow, and it gets maximum points, 100 out of 100, if it doesn't collide with the walls. If when the pair of objects falls, the robot is sufficiently far to the left or sufficiently far to the right that it doesn't touch the object, that's the best thing it can do. If the pair of objects is coming down and the gap is too narrow for me to get through and I'm panicking, I don't quite know what to do, I move away, come back, move away, come back, and I get hit. At the moment I get hit, they compute the horizontal distance, d sub I, between me and the center of the pair of objects. What's the intuition for this term? What is this term doing in the fitness function? Is evolution trying to minimize d sub I in this case, maximize d sub I in this case? We always want p and p sub I to be higher, more performance.
Minimize.
Sorry?
Minimize.
We want to minimize d sub I. So we minimize d sub I would be 0. I'm right underneath the pair of objects. The gap between the pair of objects is too narrow for me to get through. I get hit. That's the worst possible thing the agent can do.
I guess maximize d sub I because you want it to be like as close as it could be to getting away. Like you want it to be like barely getting hit, so it like almost made it out of the way.
Absolutely. So this d sub I is like a reward term. If you get hit, when you get hit, the more d sub I, you do better. Imagine two CTRNNs, two random CTRNNs in the first few generations of evolution, and those CTRNNs are causing the robot to freak out and go all over the place and barely pay attention to these incoming 7 values, and one of them gets hit directly overhead. Bam. D sub I is 0. That CTRNN did cause the robot to do the worst possible thing. Some other one that kind of got out of the way but got hit on the side of the head, that one has a greater value of d sub I. That one did a little bit better. It's slightly less crappy than the one that got hit directly on its head. So that one survives and produces some offspring. The one that got hit squarely in the head, deleted and is gone. If we fast forward this evolutionary process, you start to get robots that are still getting hit, but they're further and further away from the blocks until some offspring doesn't get hit at all and gets 100 points. Now we've evolved CTRNNs that cause the robot to get out of the way if the gap is too narrow for the robot to pass through. Everybody see that? Okay, but that's only half of what they want the robot to do. Sometimes during these multiple trials that they expose an individual CTRNN to, sometimes the pair of objects has an overly narrow gap, like we just talked about, and sometimes the pair of objects has an overly wide gap. The gap is passable. In that case, if the gap is wider than the robot gets 0 points if it's beyond the blocks. It doesn't get hit, and the pair of objects is both objects are either to the robot's right or both objects are to the robot's left. 0 points. That's the worst thing you can do. If you can get through the gap and you chicken out and you run away, 0 points. If you happen to be between the blocks and the blocks fall on either side of you, you are narrower than the gap. You don't touch either block. One falls on your left and one falls on the right. You get maximum points. If you get hit, you get these many points. What is this term doing? What is this term causing the evolutionary algorithm to do? What kind of behaviors are favored here? What kind of behaviors are frowned upon?
You do better the closer you are to the gap, to the center of the two objects.
If you get hit and you have a high d sub I, you're almost outside the pair of objects. You're almost beyond the pair of objects. That's bad. You were kind of running away and you got caught. If you produce offspring that get hit, but they're a little closer to the center, your children get slightly higher fitness than you do, and they're probably going to push you out of the population and produce children of their own that are getting hit, still getting hit, but with lower and lower Ds until eventually one child gets 100 points, doesn't get hit. Yeah? Okay, so armed with this fitness function and the CTR and N we just described, and this agent and this very, very simple simulator, you'll notice that this paper was published in 2000. This was the year that physics engines were introduced. So the authors just wrote their own code. They didn't realize it, but they were creating a physical simulator at the time, a very, very simple one. Yeah. Okay, so they evolved, and eventually they evolved one CTRNN that had very, very high P. For that CTRNN, if they put that CTRNN inside the robot, and every time they dropped a pair of objects with a narrow gap, the robot generally ran away, and every time they placed a pair of objects with an overly wide gap, the robot would get underneath and thread the needle. Again, my apologies. It would be wonderful if we had a video of this behavior in action. Some of you might want to tackle something like this for your final project. We're going to have to content ourselves with looking at the raw data. Okay, what did they do? In this particular case, we're looking at data from one CTRNN, the champion, the highest, the most fit CTRNN after evolution. So we're skipping over the evolutionary algorithm all itself, and we're going to see how good that evolved solution is. They took that evolved CTRNN and they dropped it back into the robot thousands of times. And in all those trials, sometimes the relative aperture width was 0, meaning the width of the aperture, the width of the gap between the pair of objects, was exactly as wide as the robot's width. Sometimes the relative aperture was a little bit wider than the robot, and sometimes the aperture was narrower than the robot. Okay, that's what they're plotting on the horizontal axis here. For all those thousands of trials, what was the shape of the object relative to the individual? The vertical axis reports final horizontal separation. How far to the left or to the right of the robot was the robot from the gap? So basically on the vertical axis here, they're plotting absolute D. Everybody see it? Okay. What does this CTRNN cause the robot to do? Exactly. I already told you that this evolved CTRNN generally causes the robot to run away when the gap is too narrow, and it generally tends to thread the needle when the gap is wide. But this data sheds a little bit more light, a little bit more detail on the behavior of this robot. What is it doing? Let's start with the left part of this plot. So the left part of the plot, the aperture width is narrower than the robot. What does the robot do? What does the vertical axis tell us? It goes away, right? So generally, the robot is 40 distance units away from the pair of objects when they hit the ground. It doesn't tell us whether the robot's 40 to the left or 40 to the right. It doesn't matter. But generally, it runs away. What about the right-hand side? What is the right-hand side of this panel telling us? D sub I is close to 0, which means the robot is much closer. It's threading the gap. What's happening in the center of the panel here? What is that? The data near the center of the panel, what is it telling us? What does the robot do when the gap is exactly the same width as the robot? That's what this little dot here is telling us. What does the robot do in that subset of thousands of trials in which the gap between the pair of objects is exactly the same width as the robot? It doesn't thread the needle. It runs away. It's not quite 40, but it's hightailed it out of there. It's gone. Makes sense. If you're exactly the same width as the aperture, you're going to hit the aperture. You can't really get through. What about this dot down here? This dot represents the average behavior of the robot when the aperture was just a hair's breadth wider than the width of the robot. What does the robot do in that case?
kind of looks like a 50-50 shot, whether it runs away or it goes for the.
These long horizontal bars here are error bars. So the dot here is the average. So they dropped a whole bunch of object pairs that are slightly wider than the robot. And sometimes the robot ran away, and sometimes it tried to thread the needle. So this graph is not perfectly symmetric. What does that mean? The tricky part here is obviously in the center, when the gap is almost the same width as the robot.
It seems like it likes to run away a little bit more.
It likes to run away a little bit more. Kind of a smart thing to do. You are all sitting here today because your ancestors, when they weren't sure, they ran away. Best thing to do in the cases of uncertainty, you're out of there, right? Other organisms said, well, there's a leaf moving, maybe it's wind, maybe there's a predator behind the leaf, it's probably wind. They're not here to tell us their story for exactly that reason. Interesting. Again, this is a minimally cognitive agent. This is about as simple as you can get, but it's already exhibiting certain sort of eccentricities. This is not an optimal robot by any means. When the gap is slightly wider than the robot, optimally, according to this fitness function, the robot should always thread the gap, but it doesn't. It's a non-optimal agent, but most humans and organisms that can understand what's going on here would kind of nod and say, you know what? It's doing the right thing. Some of you might have heard of the alignment problem in AI. This is a growing realization that we don't really want optimally smart machines. We don't want them to be maximally rational. We want them to be non-optimal in the way that we would be non-optimal. If you want to survive and thrive and be safe to yourself and safe to those around you, there's certain deviations away from optimal behavior that we would like. And why it's called the alignment problem is it's hard for humans to actually know what these things are before the fact. Here's an example of that. Just again, this was a very early study, but it's a glimmer of AI alignment. We have a robot that's not optimal, but it's doing what we would probably do in those circumstances. A good sign. Okay, we've got a little bit of time left. In these experiments, we're going to see 4 different building blocks of cognition. That was the first one. Oh, sorry, we haven't finished with this one yet. One other interesting aspect of this experiment. Let's have a look at these plots over here. In this case, they're going to, again, take that same evolved CTRNN, the highly fit one, the one that causes the robot to do this. They're now going to drop pairs of objects, more pairs of objects from the top of the screen. And in this panel here, that pair of objects had a gap that was too narrow for the robot to get through. And in these object pair drops, the aperture was wider than the agent. The aperture was passable. In this set of the experiments, they dropped the pairs of objects from different horizontal positions at the top of the screen. Here, then here, then here, then here, then here, and so on. So they're going to plot on the horizontal axis here at every point in time in the simulation as the pair of objects is falling. At each time step in the simulation, what is the horizontal position of the robot relative to the pair of objects? The vertical axis here is reporting the vertical position or the height of the pair of objects. So let's follow one of these trials. Let's follow this trajectory that starts in the top left. So the pair of objects is placed 140 units above the agent, and it's placed minus 40 units above the robot. So the pair of objects starts falling up and to the left of the robot. So far, so good? For this particular pair of objects, the gap is not passable. The object starts falling, and we're going to follow this trajectory. Look at the shape of this trajectory. What is the shape of this trajectory telling you about what the robot starts doing?
It moves towards the pair of objects.
It's starting to go towards the pair of objects. This trajectory is mostly vertical for the first 40 units as the object is falling. So the object is looking at it, and it's slowly moving towards the object. And then, as you said, the slope suddenly changes, and the robot speeds up and starts heading towards the falling pair of objects. Let's follow this trajectory down. What happens? What's happening at this point? What does the simulation look like at this point in time?
The robot has concluded that it's not passable, so it'll start moving away.
Ah, okay. It has concluded that the object is not passable. Maybe. What we do know for sure, and it's hard to see what's going on in this little traffic jam here, this trajectory continues down here, and down here. We end down here at the right. What happened at the end of this particular simulation? You mentioned it already. The robot ran away. The robot ends up 40 units to the right of, or whatever, to the left, the other side of the pair of objects. So it started by the objects were up and to the left. It moved underneath, and then just kept on going. It seems obvious that the robot decided or made a decision that the objects were unpassable and ran away. When? When did it make this decision? When did the robot know that the gap was unpassable?
When it was right under it.
When it was right under it. Why? How do you know? How do you know it didn't make the decision here or here? How do you know it didn't make the decision here?
Well, it started off already outside of the center of it because it was to the left.
Okay.
And then it moved towards the right.
Yep.
Saw that it was underneath, and then it moved way faster towards the right.
Okay, so maybe the speed of travel is the signal that now it knows. When any of these trajectories is vertical, that's the robot staying still. The pair of objects is falling straight down, and the horizontal distance is not changing. Maybe when it's still, it doesn't know. And maybe when it goes fast, that's when it now knows.
Well, it also wouldn't make sense for it to know until that point because it was moving towards them.
Possibly. The robot, remember, it has these long whiskers. So as it's moving, those whiskers are brushing the object, or they're breaking these proximity sensors. The infrared pulses are coming back faster. So it can see both objects. Possibly it's inferring the distance between them. Maybe. Hard to say, actually. The more you think about it, the more tricky it is to say with confidence when it knew. It must know because it ran away. Or maybe it always runs away. So maybe it actually doesn't know. So let's hop over here for a moment and let's do the same thing. In this case, they're going to drop a pair of objects from above. The robot is 40 units to the right of the objects. The objects start falling. In this case, the gap is passable. The gap is super wide. The robot could in theory, could thread the needle. What does the robot do in this second trial compared to what it did in the first trial? Follow this left-hand trajectory.
I mean, it's pretty much the same thing. It just ends up staying at that.
It does pretty much exactly the same thing all the way up to this point. This trajectory is almost exactly the same, as this trajectory. And then something different happens when the objects are only 60 units above the agent and the agent's underneath. What does it do differently?
I think, it's scanning above it, and the middle whisker or whatever sees that the gap is big enough. Because it goes past center, so it goes past, sees that the gap is big enough, and then it aligns itself to the center to make it through the gap.
It overshoots a little bit, right? It scans underneath and goes and stops and comes back and then stays completely still and shows off. It gets in position 40 while the pair of objects is still 40 units above and just waits. It looks like it's getting underneath, and maybe it's got something to do, maybe it's relying heavily on the middle whisker that's pointing straight up, which now is no longer obstructed. That proximity sensor is shooting right through the wide open gap. Maybe it's around here that it makes the decision. Maybe. Okay, tell me about the other trajectories. They give you a sense of what the robot is doing in general. You can see that in general, when the gap is passable, in every single one of the cases, no matter where they dropped the object pair at the top, the robot always threaded the needle. What did the robot do when the gap was unpassable? In general, what did it do?
It always moved away.
It always moved away. Half of the time it ran away to the left, half of the time it ran away to the right, and its behavior is symmetric. Kind of interesting. If you look at the top, if you look from 60 to 140 in both panels, they're indistinguishable. The robot, regardless of whether the gap is passable or not, if you observe the robot's behavior in those in that first half of that simulation or so, the robot isn't acting as if it knows whether the gap is passable or impassable. So does the robot know or not? Could it, in theory, know? Sure, it could know. It might know long in advance before that point whether the gap is passable or not, but it's not telling. I didn't mention this detail, but in these CTRNs, which are fully connected, you've got a fully connected network, which means you have a lot of self and recurrent connections, which means the robot has memory. Maybe it's sweeping or brushing its whiskers underneath these distant object pairs, and it's actually made the decision. It knows, and it's holding on to it. But whatever that internal pattern is that it's remembering, that internal pattern slowly doesn't take control of the motors until this point. It is impossible to tell from these behavior traces. We're just watching the movement of the robot relative to the object pair. It is impossible to say when it knows. It is possible to say it knows because it consistently does the right thing in these two different conditions, but who knows?
Could it just be the processing time? Because it seems like it just moves regardless. It just tries to run away. And then until it brushes up against the thingy, it's still running away, but then like the whole process finishes and it's like, oh, I can go back and stay here, you know?
Possible, but have a look at when things were dropped from the upper left, the robot moves to the left. Mm-hmm. When objects are dropped from the upper right, the robot moves to the right. So the robot is already showing us that it's paying attention. It sees the object pair, and where it sees the object is influencing how the robot moves. So it is definitely not processing speed. It's already reacting to the object pair in some way, but whether it knows about the affordance or not, or when it makes that realization is not clear. Tricky. We talked about the Libet experiment from the 80s a few weeks back. People look at a moving dot on a thing and they say, I made the decision to move my finger at exactly that time. I know it. I know I made that decision at that time. They didn't. Unawares to them, some other part of their brain, not the conscious part, made that decision somehow long before. Similar situation going on here. Hard to say. Again, kind of interesting. There's nothing in the fitness function that said, you must act differently when you decide. You must compute the passability affordance and store it in this part of the brain. There were none of those explicit instructions. So it gives us a little bit of a mystery, like us. When and how do we make decisions? And when do those decisions start to outwardly affect our behavior? Hard to say. We'll talk about this final analysis of this evolved CTRN next time. You have a quiz due tonight. Undergrads, you're working on A6. Grads, you're working on D1. See you next week.